The screen is visible to all.
Yes, sir.
Okay. So today we are discussing with fifth module, that is last module of fluid mechanics. So just will go back to the syllabus once again. In the last module, we have laminar flow and its viscous effects. In that, we are going to discuss about the laminar flow of the fluids. Okay, in the entire syllabus, we are not discussing turbulent flows. So laminar flow will be discussed here. So that is in the pipe, entrance and developed flow we are going to discuss. Fully developed laminar flow and Hagen Poiseulles equation. So we will understand what is this equation and how to derive this, the pressure difference between pipe flow. That is called as Hagen Poiseulles equation. Then later we are going to discuss some numericals on this chapter. So this is one chapter in which we are going to discuss about laminar flow with some viscous effects. Next we have a small chapter, that is flow past immersed bodies. Very simple chapter. So here we are going to discuss about drag, lift and expression for these two, drag and lift of different bodies. Then with simple numericals we are going to understand how these drag and lift forces are going to work with the bodies, so that lift or dragging can happen with the given different bodies. So that is a very small chapter. This chapter is very small. So without derivations, we have to analyze this chapter. Then last chapter, we have introduction to compressible flow. So until now, what we discussed up to, say for example, laminar flow, we discussed about all about the liquids which are incompressible in nature. So to give some introduction, we have last chapter, that is part of module 5, compressible flow. In that, we are not discussing anything introductory part of compressible flow, because already I think in physics or in our introductory subjects before Bachelor of Engineering also, you might have come across the equations relating the gaseous flow or the compressible flows. So that we are not learning once again here. Directly we are taking the propagation of sound waves through a compressible fluids, or the disturbance in the compressible fluids that we are discussing. And we are discussing the sonic velocity and Mach number, that is subsonic flow or supersonic flow. So such type of flow, how the disturbance of the sound waves are going to be affected in this type of compressible flow. So that we are discussing in this compressible flow with some simple numericals. Okay, this is all about the fifth module. So we'll start with the laminar flow today, and later we'll go to the flow past immersed body. Last we'll take the compressible flow. Okay, these all three chapters are independent in nature. All three are not related to each other. But earlier, what we seen in the kinematics, dynamics, or measurements of fluid flow, all are related topics to each other. But here, even we can start with flow past immersed bodies, then you can go to compressible, or you can go to laminar flow. Okay, the series may be different. So today we will start with the laminar flow. So in this laminar flow, first of all, what you have to do is, first you have to recall the Reynolds number. Without Reynolds numbers, one cannot differentiate what is laminar flow or the turbulent flow. So even you have done the experiment on the Reynolds equation. So from that experiment also, we come to know that how to find out the Reynolds number using the pipe flow with some velocity and discharge. So one can find out the velocity of this Reynolds number And based on the Reynolds number, one can differentiate whether the flow is laminar or the turbulent, or it is transitional flow. So in such conditions, the viscous forces or the viscous effects are more when the flow is laminar. So in this uh, chapter, we are going to discuss about the laminar flow with viscous effects in the pipe flow, and one more is the flow between the plates. So these two things we are going to discuss in this chapter. So coming to the introductory part, all of you know that many fluids are viscous in nature. So in case where viscous effects is negligible, in such conditions the flow can be treated as ideal fluid, okay, which is not a Newton fluid, because any fluid which is not viscous in nature, it is not having any resistance. Okay, so such type of fluids are also called as non-Newtonian fluid or the ideal fluid. And the fluid must be treated as a viscous fluid when it is having some resistance in the fluid. So the flow in a conduit, so conduit in the sense it is a closed channel, or you can call it as a duct flow or a pipe flow. So whenever the circular cross sections are there, the majority of the time we consider pipe flow itself, because manufacturing uh, costs are less for the pipe, and also it is very easy for construction or the fabrication purpose. So here in the chapter also we are going to consider the pipe flow. Okay, so that is classified being laminar or turbulent depending upon the magnitude of the Reynolds number. So as I told you, go back to the Reynolds number. So depending upon the type of flow, one can understand whether in the laminar flow, whether the flow is very smooth and it is a streamlined flow, and all the layers of the fluid are flowing relative to each other. So in the pipe, also we know that viscosity law or the Newton's viscosity equation, we know that at the center of the pipe, the velocity will be very high. And at the walls, because of the viscosity and the resistance of the wall surface, the velocity at the pipe surfaces, inside surfaces, will be very low. Okay, so due to that, what happens? The velocity fluctuations will be there, and it will be in highly disordered motion. If it is a turbulent flow, and velocity will be very a proper way, such that by equations we can define the velocities. In that conditions, it will be a laminar flow when you can define the velocities. Okay, and in the transitional flow from laminar to turbulent flow, between laminar and turbulent flow, the flow occurs over some region in which the flow fluctuates between laminar and turbulent. So that becomes a difficult situation to define the flow with some equations. We cannot define the transitional flow by a proper equations. So that is one difficulty. And also in turbulent flow, suddenly the changes in the properties or the parameters of the equations are also cannot be judged easily. So keeping these all difficulties in mind, now we'll see how to understand this laminar flow and viscous effects in a given pipe flow. So just again we'll recall once again the Reynolds experiments here. So I'll not recall about the objective or apparatus used here. So generally we know that whenever without using the Reynolds number also, if the flow is smooth, or the whatever the dye or the ink is injected at the center, if it is flowing with a straight line at the center of the diameter of pipe, okay, or wherever the dye or the ink is injected, at that position only it is maintained up to the exit. So if the flow is completely straight, then we can understand that is a laminar flow. And slowly, if it starts changing its path, or uh, without mixing, if it is flowing in a different diametrical or radius path, then we can say that it is a transitional flow. Then later on, once you increase the velocity of this liquid by opening the wall at a more diameter and injecting the dye again here, what happens? After some distance, the fluid starts mixing. The fluid starts mixing in the sense it starts moving in different directions, and it will leave the path of the center. And due to this mixing, what happens at the discharge, we cannot separate, or we cannot properly distinguish between the water and the ink. In such conditions, we can just by seeing it or by visible effects, one can say the flow is a turbulent flow. So like this, depending upon the path of the fluid inside the pipe, one can just visualize without using the equation of Reynolds number, just by observing a transparent tube inside the pipe, how the flow is going to take place. If you supply some dye or a ink or a color fluid, which is not mixing with water exactly, so the path of that particles, if you observe, one can explain whether the flow is laminar, transition, or a turbulent flow. So this is about the Reynolds number what you have studied already. Now later we have to understand how these viscous effects are going to come into picture in the laminar flow, due to which there will be a head loss, pressure loss, okay, or there will be some shear forces. So many parameters will be there in this viscous effects in the laminar flow. Just a minute. So until that, you can just note down the sketch and the different factors which are written in the sketch here. And note down. Yes. So here we need to consider a horizontal pipe that is given here of radius r, or r radius of the pipe is given here. Then a viscous fluid. This is very important here. We need to consider a incompressible viscous fluid which is flowing inside this pipe of radius r or capital diameter that is given, okay, in the direction from left to right. So that direction is also given here. So considering a fluid element, so again, as in the Euler's equation we have seen, we have to consider a cylindrical element here of the fluid. So the entire flow volume, we are going to consider a small area of the small volume, that is called as dA or the dB, small volume or the small area. Later we can integrate and you can find out for the complete flow how the pressure drop will be there. Understand? So before that, we are going to consider a small element. So for that, we are going to call about the small distance dx, small area dA, okay, or the small volume of this cylinder as a dV. So that small element is considered of cylindrical object, okay, at a radius of small r. So that small r is equal to the radius of the given cylindrical object, which is considered for the derivation. Okay, and thickness of this small ring on the cylindrical object, that thickness is shown in the side view. So that thickness is a dr, small dr, and the length of this element is considered ds. Then the P intensity of the pressure acting on the face AB, on the face AB, the force acting is P into area, pressure into area, that is P into pi r square, because that pi r square is nothing but a ring area, because the small ring we have considered for the external surface radius. Okay, so for that we have considered the area as P into r square, pi r square. Then the pressure force on the opposite side, which is resisting. So I can just assume this cylindrical object is going to flow in from left to right side. When it's flowing from left to right side, before flowing, assume it is in stagnant condition. The flow is not taking place. Once the flow starts, what will happen? There will be some shear force acting on the surface. Also, there is some resistance which is opposing the flow. So that resistance which is opposing the flow in terms of force is nothing but pressure which is acting at a distance of dx from EB. So that we are considering the added pressure, that is P plus rho P by rho x is the small change in pressure at a distance dx. So rho P by rho x into dx into area of the surface of the ring cross section area to see, that is around pi r square. So these two pressure forces are observed in the flow direction and opposite to the flow direction. So that are listed here. The pressure force on face AB is P into pi r square. The pressure force on the face CD, which is opposing the flow of this fluid element in the given pipe. That opposing force of the pressure force is P plus rho P by rho x into dx into pi r square. Now, whatever the shear force is acting, that is going to resist at the surface of the cylindrical object. So, on the circular ring of small radius r what is given outside ring, on that surface, the shear force is going to act. So, that shear force is represented by tau. Okay, this we have already studied in the first unit of Newton's law of viscosity. Tau equal to mu into du by dy. The same shear force is considered here. Tau is acting on the surface area of this cylindrical object. So that surface area is equal to 2 pi r into dx, because it is having thickness of small radius dr. Sorry, that is length. Total length is dr, and that small r, whatever was there, it is taken for the surface area, 2 pi r. To find the surface area of the cylinder, 2 pi r is taken here, and the length of the cylinder, to find out the total surface area of this cylindrical length object, there they have multiplied with dx, length dx. Okay, it is nothing but 2 pi d into L. Okay. 2 pi d in terms of t, it is r is given here. L is given in terms of dx. Is the dx is the length of the small element in the cylindrical form. So these are the three forces which are responsible when the flow is incompressible and the flow is viscous and it is in laminar condition. Okay. So taking these all equations, now we are going to balance. So for equilibrium condition, the sum of all these forces in a given one direction, you can equate it to 0. So in next direction, if you consider, as I have considered the flow is in next direction, so the sum of the pressure forces, viscous forces in the next direction must be equal to 0 to balance all the effects. So that is written here. P into pi r square minus P plus rho P by rho x dx pi r square minus. So why minus sign is taken here? Because these shear force and the pressure force on DC, these are the three forces are opposing, or the two forces, shear and pressure force, are opposing the flow. Okay, and P, the pressure whatever is applied because of the flow, that is positive direction because it is flowing in right side, and these two forces are flowing applied in the left hand side. So I'm taking minus tau into 2 pi r dx equal to 0. So once you simplify this equation to find out the tau, so tau can be found out by this equation after cancelling the pi value or remaining the p values. You cancel it because this p into pi r square minus p into pi r square can be cancelled. So we left with minus rho p by rho x into dx into pi r square. Okay, so similarly minus tau into 2 pi r dx. So this dx can be cancelled later because of the minus signs of the positive signs. So finally we'll get tau equal to minus rho p by rho x into r by 2. So this will be our shear stress equation. You can note down the shear stress applied in the viscous flow in laminar condition on a small cylindrical object will be minus of, because minus indicates the direction. In opposite direction it is applied the flow opposite, that is rho p by rho x into tau r by 2. So this equation indicates the shear stress distribution across a section. I'll repeat once again. The pressure force which is already present because of the flow, that is P into pi r square on this area AB. Then we have opposing pressure force on the other side, which will be little bit addition of this pressure, that is dou P by dou x into dx at a distance dx. Okay, and the shear forces are also opposing the flow. So I am writing that shear force as tau into 2 pi r dx equal to 0. Now if you cancel P into pi r square minus P into pi r square, I left with minus dou P by dou x dx into pi r square minus tau into 2 pi r into dx equal to 0. Okay. Now if you cancel the remaining terms, we left with minus dou P by dou x into r minus 2 into tau. What we cancel? We cancel pi r on both sides and dx on both sides. So now we left with tau equal to minus dou P by dou x into r by 2. This is the shear stress on cylindrical surface. So by this equation, you can just observe as the radius increases, okay, as the radius increases, the magnitude of the shear stress is going to increase. So at the wall, the shear stress will be very high. At the center of the pipe, okay, at very low values of R, the shear stress will be minimal. So that is shown with this graph. And velocity already you know how the velocity distribution will be there. So as the center of the pipe, if you consider, the velocity will be high due to the low resistances. And once the flow nears or the laminar flow, the particles which are near to the wall, the velocity will be very less because of the high resistance. So that is again explained here. Maximum shear stress can be found out by using the full radius R. Capital R can substitute in the same small radius here, because this radius was taken for the one small element of cylindrical object. If you consider for the full pipe cylindrical object with full radius, that is small r equal to capital R, then tau we can write it as tau max, because once you find out the tau max at full R, the value will be very high. Okay, so tau max I can write it as, if you are finding shear force at the surface of the pipe, the full flow radius, then I can tell the tau max value is minus dou P by dou x and R value what is given here by 2. It is the same line of this equation only. This small is are for the small element. This they have taken for defining at complete surface of the inner surface of the pipe what will be the shear force. So it will be maximum. To tell that maximum, we have written tau max. Okay, now we'll see the velocity distribution. As in this sketch is shown, velocity at the center is maximum and at the wall is minimum. So how it is defined? So again, recalling the Newton's law of equation for viscosity, that is tau equal to mu into du by dy. So here already you know mu is the viscosity, dynamic viscosity, u is the velocity of flow, y is the distance from the uh, center. It is the pipe. It is the plates, distance between the plates. Consider y. The value y is measured from the pipe wall. The wall to wall distance can be measured as y. Okay. So if you consider a small distance dy, so for that we can consider here the distance between the small element and between the full pipe. If I take, I can write it as capital R minus small. Okay, because we are focusing on the small element of the cylindrical object. So for this cylindrical object, the velocity if you are finding, I can find out velocity between or distance between these 2 points. That is capital R minus small r. So if you are finding like that, I can consider that change in distance as dy. equal to minus dr. So 0 they have considered for the full radius, and the change in radius, whatever is there, they have taken dr, minus dr, just to replace this dy term. I hope you are getting. Say for example, if I consider for small dr, so that small change in radius. Now, in the linear direction, if you take, now in the problem it is circular. If you take linear dimensions between the planes or between some height, then I can replace this small dy term as dr in the circular type. So that they have replaced here. Now Newton's law of viscosity is defined for a pipe. So for a pipe, I can write it as tau equal to minus mu into du by dr, because distance y is changing in this pipe in terms of minus dr. So now you can equate or compare these two equations. That is 6.1. 6.1 is tau of the shear force equation, general shear force equation. Tau equal to minus dou p by dou x into r by 2. In place of this, I am going to substitute this equation number 6.4. That is tau equal to minus mu into du by dr. If I just compare both the equations, now it will be minus dou p by dou x into r by 2 is equal to minus mu into du by dr. Just you can replace some term and see the heading. What was the heading? Heading was we need to find out the velocity distribution. So in these two equations, what was the velocity? Velocity term is only du. So I want to find out what is du value. So for du, I can write as du equal to 1 by 2 mu dou p by dou x into r into dr. I'll repeat once again. The velocity distribution term, that is du, can be written as 1 by 2 mu, okay, 1 by 2 mu dou p by dou x into r into dr. So this dr I am putting here. That equation we are going to find out, and where minus signs will be cancelled. Now I can tell after integration for full volume of the flow, what is the velocity distribution equation. So that if I integrate this equation, the whole equation, now I can write u equal to 1 by 4 mu dou p by dou x into r square, okay, r square plus c. So finally, if you integrate r into dr, it will be r square by 2. So in the same fashion, after combining all terms, after integrating, I can write it as 1 by 4 mu into dou p by dou x into r square plus c. C is the constant. You can note on this equation of velocity distribution. Until now, we saw the shear force distribution in small radius r, the shear force distribution at full r maximum value, and also we saw the velocity distribution, that is u, equation for u in the pipe. Now, if you want to find out the constant, as you already know, to find this constant, I can take this constant on one side and equate all the terms on other side, so that you can find out constant. So similar fashion, they have taken applying the boundary conditions, that is, if small r is considered as capital R, so for a full pipe, the small r is considered for full R, then velocity, if you see, velocity at the full R is 0. So if I substitute those boundary conditions in this equation for C, I can write it as 0 equal to, that's because velocity is 0 at the wall, 1 by 4 mu dou p by dou x, small r is equal to capital R square, full pipe radius, plus C. Now I can tell C is minus 1 by 4 mu dou p by dou x into capital R square. This is the constant of integration value. So if that is in minus terms, velocity will be 0. Okay. If velocity is having some number, this constant value will be different from this equation. So this equation is found out at the wall of the pipe. At the wall of the pipe, velocity is 0 and small r is capital R. So this equation again if you substitute for the full radius and small radius separately. Okay. So here we have used small r and capital R, both equations. So what we get? We can write it as u equal to minus of 1 by 4 mu dou p by dou x into bracket r square, capital R square minus r square. So by this equation, one can find out velocity at any given point. Okay, at any given point means either you can find out the velocity at the center, if you know the capital R and small r at this point. You can find out the average velocity at a given distance because average velocity of this pipe flow, if you see, center it is high, wall it is 0, and in between we may get some average velocity. Because we are finding the distance, if you see, always we are taking some velocity at the flow. But that velocity is not at the center or is not at the wall. Okay. So for discharge value, if you are using the velocity term, that velocity is the average velocity. So for entire cross-section area of this pipe, what is the average velocity here? Based on that, we are going to find the discharge. So for that, we want average velocity as in the negative case. The values of this new dou p by dou x and r is the constant because these are the fixed values. Okay. And velocity u varies with the square of r. See here, it is varying in the square terms. All equations, if you see the velocities, it is varying in terms of square. So that's why this parabolic curve will be there for the velocities. But for the shear force, it is directly proportional. It will be varying in linear fashion. Okay, so here r curve is not a square, and it is changing with respect to x and directly proportional to r. Like that, it is varying in linear form. Okay, now by using the same equation velocity, so at what position the maximum velocity can be defined. So for that, I can substitute the boundary condition, that is at r equal to 0 here is the above equation, and put r equal to 0, small r equal to 0 at the center of the pipe, and u or the velocity you can term it as u max, because in this equation if r value is not there, then the total velocity will be written as it is, which is maximum value. So for the maximum velocity, boundary condition will be small radius r should be 0, means we need to consider only the wall radius, capital R. So this equation, if I write in using only R value, capital R value, then it will be U max minus 1 by 4 mu dou P by dou x into capital R square. So if this capital R square is not subtracted by any term, then the velocity in the pipe will be maximum. At what point? At the center point. At center, the velocity will be maximum. Okay, where the small r value is neglected. Next is the discharge through pipe. So for this we need average velocity. All of you know the discharge how to find it. See, all these things we are finding finally to find the pressure drop between the pipe. So that pressure drop between the pipe at inlet and outlet, if you see, that is called as Hagen Poiseulles equation. So to derive this equation, we are finding all these different terms. Okay. To discharge, all of you know, for a given element, cylindrical element again, dq, small cylindrical object, the discharge through that small element of cylindrical object is given by velocity at radius r, the small element, into area of the flow. So that area is here is, it is area of the elementary ring. So area of the elementary ring is already told, it is 2 pi r into dr. and velocity at radius r is u. But what radius we have taken u, that we don't know. Just one rough element of cylindrical object is considered. For that, we noted it as small r. At this r, the velocity is assumed as u. The value we don't know. So whether it is average velocity, maximum velocity, or minimum velocity, that we need to find out by the substitutions. Okay. So using these terms, dq equal to u into 2 pi r into dr. So already you know the equation for u, the above substitutions. So u term I'll recall here. This term I can recall, and I'll write minus 1 by 4 mu rho p by rho x into bracket capital R square minus small r square into area of the elementary ring. That is 2 pi r into dr. So in that section, we are assuming the flow is taking place for a small cylindrical object in this ring. This is the ring of this dr. The flow is taking place. Okay. So for that area, we have taken 2 pi r into dr. So as you know, to find the total discharge, you can convert this dq into total q by integrating from 0 to r. That is from center to full pi. Once you integrate this term dq, on the right hand side, I'm going to integrate between 0 to r minus 1 by 4 mu rho p by dx into bracket r square minus small r square into 2 pi r into dr. After integrating, what all changes will be there? So constant values we are going to separate, and we are going to integrate only of radius terms. So once you integrate, I will get r raised to 4 by 2. Okay, because here small r after integrating, it will be capital R. Okay, putting those 0 to r, either it may be 0 or it may be capital R. Once you substitute like that capital R and small r after differentiation, the final term will be minus pi by 2 mu rho p by dou x into bracket, we just focus here, r raised to 4 by 2 minus r raised to 4 by 4. This will be the terms after integration. So these are the variables, these are the constants. Left side are the constants. Inside bracket are the variables. So now if you take the LCM, I can write the discharge, total discharge equation in terms of viscosity as minus pi by 2 mu rho p by dou x into r raised to 4 by 4. You take the LCM and take the differences, that is 4 into r raised to 4 minus r raised to 4. That is r raised to 4 divided by the LCM. That will be 4. Okay. So now total discharge, you can write it as, so multiplying all the terms at the denominator, that is minus 5 into rho p into r raised to 4 divided by 8 mu ds. Or in separate digital, it will be minus 5 by 8 mu total discharge through a pipe in the laminar flow in terms of viscosity and pressure difference. Because until now, in the flow measurement, you have taken area and velocity directly. Okay. But here we are considering the viscous effects, and we are assuming the flow is in the laminar condition, and there is some pressure difference between the flow. So in such situations, how the discharge is measured? Discharge is measured minus 5 by 8 mu rho p by dou x into capital R raised to 4. So this will be the total discharge equation for a laminar viscous flow fluid. So this equation we have found out again by considering the area and velocity of the flow in terms of viscosity and pressure difference. Now after this, as I told you, we also made the average velocity for this. Again, the same equation Q is used here for finding the average velocity. And for the average velocity, they have denoted it as U bar. Or can write U average. See here. To find again the average velocity, because here, whatever the terms we have taken earlier, it was in the normal velocity between 0 and capital R. But here, what we have done, we have taken to find the average velocity. At what point the velocity will be average. Just a minute. Am I audible?
Yes, sir.
So until now, we have found out the velocity at the center, velocity at the uh, surface of the pipe or the inner surface of the pipe, that is Umax. Then using this discharge equation, we are able to find out the average velocity. Now until in this subject, we all know only this at the center and at the wall. But what about in between velocity? So for that, we have relations of equations, but we until now we have not found out what is the average velocity point or exact location. So for that, to find out in equation form, so later in the problems you can see the problems which where you can find out where exactly the average velocity point is. Okay. No doubt it is in between this maximum and minimum. Average velocity will be between this maximum point and at the minimum point. It will be here, somewhere here it will be there. But where exactly it is located, it is defined by this equation. So for that, we have considered here. U average can be found out by taking Q by cross section area of the flow. So here, either you can go by the small cylindrical object and you can again integrate, or else, as you already know the complete cross section area of the pipe, as well as you also know the full discharge equation. Already you have derived. No need to go by using this change in radius or the change in radius or strength terms for the not integrated form. That also you can take, and again you can integrate and find out. That's also possible. But here what they have done, directly Q and AC equations are available. So they have taken Q as minus 5 by 8 mu dou P by dou x into R raised to 4 divided by area of the cross section. So that they have taken. Now you can see the average velocity Umax at what location or at what is the magnitude of that average velocity is minus 1 by 8 mu, okay, 1 by 8 mu dou P by dou x into R raised to 2. So that R raised to 4 and R raised to square is cancelled, and phi is also cancelled here. That's why the final equation is minus 1 by 8 mu dou P by dou x into R4. So if you know the radius of phi, pressure difference, distance at which the average velocity you are finding, linear horizontal distance dx, and viscosity of the fluid. If you know these things, one can find out the average velocity magnitude. Okay. So now, how much this maximum and average velocity are different, or how much is the change in the values? So to find that, now they are going to take the ratio of the maximum and average velocity. So what is maximum velocity equation? Maximum velocity equation is found minus 1 by 4 mu into dou P by dou x into R square divided by average velocity U1. So here in this U1, that is minus 1 by 8 mu dou P by dou x into R square. If you is the ratio. Now I can tell what is the magnitude of maximum velocity and the average velocity. So once you take this ratio, 1 by 4 mu divided by 1 by 8 mu, dou p by dou p by dou x can cancel. R square common term can cancel. So finally we left with 1 minus 1 by 4 minus 1 by 8 minus minus can cancel. Okay. So later I can write it as 8 by 4. So 8 by 4 if you simplify, I will get the ratio of maximum velocity U max to the average velocity U bar will be 2. The meaning of this ratio is the maximum velocity in any pipe if you see with laminar viscous effects, if the flow is taking place, in such conditions, the maximum velocity will be 2 times the average velocity. Is that clear? So, going back to this sketch of the image, if the maximum velocity is known, average velocity will be how much? It will be in terms of 2 times or the 1 by 2 times. I hope you are understanding. The half of the maximum velocity will be the average velocity. Almost at this position, you can find out the average velocity value. So that is defined by this equation. That is ratio of maximum velocity to the average velocity is 2. Meaning is maximum velocity will be 2 times the average velocity. So wherever the half velocity can get from the maximum velocity, that position I can tell it as a average velocity point in the pipe flow. Okay, now we'll finally come to the Hagen Poiseulles equation using all above these equations. That is, to find the loss of pressure head for a given length of pipe L. So this is very important now. Hagen Poiseulles, what he did, he used the laminar flow with all its viscous effects, and he considered small element and integrated for a full flow to find out different velocities, zero velocity, maximum velocity, average velocity. Then he also found out the discharge. Okay. So after finding all these terms, now we want to find out the pressure difference or the loss of pressure head between the 2 points. So for example, here we have taken a pipe length of L. Okay. At this L point, you have marked the pressure point 1 P1 and pressure 2 point P2, and there are 2 gauges are connected here, 1 and 2. So between these 2 points, the distance of the pipe considered is L, and at the entry or the exit you can see a small x1 is considered. So that at the entry of the pipe, what is the total length? The total length from the entry of the pipe is L plus x1, or it is called as x2. Okay, total length of the flow up to the second point is shown here as x2. So between which 2 points we are going to find out the loss of pressure or the drop in pressure. That equation defines the Hagen Poiseulles equation. Now you can see using this average velocity, that is minus 1 by 8 mu dou p by dou x into r square. Now we need to find out this drop in pressure or the difference in pressure dou p. Here we are going to focus. So taking this term outside, okay, I can write dou p by dou x equal to minus 8 mu into u bar. Here 8 mu is moved here. So it will be minus 8 mu u bar divided by r square. Because we are focusing on this change in pressure or the drop in pressure. Okay. Now if you integrate between the pressure and the distance x, so if you integrate dx, we have taken x1 and x2. Points x1 and x2. Between that x1 and x2, L is there, or x2 can be defined as L plus x1. Like that, different terms are used here. Now once you integrate, the flow equation, I can integrate dp between P1 and P2. Okay, same dx term I can take it on other side, so that keeping this 8 mu u bar and r square as constant terms. And once you integrate dx between x1 and x2, I can write it as x1 minus x2. Okay, so it will be P1 minus P2 equal to minus 8 mu u bar divided by r square into bracket. How x is changing? X is changing between x2 and x1. Okay, so that is written as x1 minus x2. So for simplifying, you can see x2 minus x1. What is x2? X2 is this point. X1 is this point. Once you take the difference, it will be n. X2 minus x1 is n. Okay, so they have rearranged the term here. So after rearranging, what will happen? This minus 8 mu u bar r square in this minus term will be replaced by replacing this x2 minus x1. Okay, now I can write the difference of pressure P1 and P2 or P1 minus P2 equal to 8 mu u bar into L divided by what is capital R square? Capital R square is only radius. If you need in terms of diameter, you can write in diameter, or you can keep radius as it is, not an issue. Okay, both are same. So if I want in diameter, I can write diameter as radius also, in terms of radius. That is d by 2. So d by 2 whole square, right? Then because of this divided by 2 in terms of diameter, now the pressure difference what will be there? P1 minus P2 can be written as 4 into 8. 4 into 8 will be 32. 32 mu into u bar into L is the numerator divided by this. This equation will define the pressure difference between the flow line. At which points? At point number 1 and point number 2 in the pipe. Okay, so if the pressure difference is asked, you can directly use this equation P1 minus P2 equal to 32 mu u bar L divided by T square. So now finally I can tell the head loss. If you want the head loss due to friction, this head loss due to pressure points. Okay, so that loss of pressure head I can tell HF as. Okay, whenever I convert the pressure into head, I have to again recall the hydrostatic law, that is P equal to rho H. If you want the head losses, so in that term, if I again recall that P equal to rho H, so that head loss in terms of pressure, if I want to put in this equation, I can write it as head loss due to pressure equal to P1 minus P2 divided by rho G, or it will be P1 by rho G minus P2 by rho G. That's here. Equal to, again on the right hand side also have to divide by rho G. So that I can write it as 32 mu into u1 L divided by rho G T square. So this equation is the Hagen Poiseulles equation. To find out the pressure head loss of the pressure difference between 2 points and converting this into head loss. What he did, he found out the pressure drop or pressure difference between the 2 points, that is 32 mu into u bar into L divided by T square, and later he converted it into head loss. So after converting into head loss, then the equation will be converted into 32 mu into u bar into L divided by rho G T square. So this equation is called as Hagen Poiseulles equation. Okay, so I think the time is 1:10, and just all of you recall once again what procedure we followed for deriving the Hagen Poiseulles equation from many different equations. So first we took a pipe. In the pipe we assumed the fluid particle flow are incompressible in nature, and the type of flow is laminar, and the fluid is viscous in nature. In that, we considered some dimensions. So what the pressure is acting on the left hand side area, pressure is acting on the right hand side area, which is opposing in nature. And also we consider the shear forces which are opposing the flow on the surface of this ring. And cross-section area of the flow we consider only this ring. Later we integrated from 0 to capital R. On the side you can see. From this line to this line, we consider total radius of diameter of the full pipe flow. And over the derivation, we found out the shear force relation tau. Then we found out at what point the tau will be max. Okay. And we started deriving from the velocities. So there are three velocities. One is normal velocity u and maximum velocity of the center and the average velocity. And to find the magnitude, we also saw that ratio of maximum velocity to the average velocity is 2. Okay. This also we saw. Then using these all velocity terms and pressure difference term in the given equation itself, we use the average velocity equation and derive the Hagen Poiseulles equation, which is nothing but the head loss due to pressure readings. Okay, after flowing from P1 to P2, there will be head loss. So that head loss we have denoted as H. So that head loss due to pressure difference is given in terms of viscosity, the average velocity, length of the pipe flow, and density of the given fluid, G value, and diameter of the pipe. Okay. So if the flow is laminar viscous, you can use this equation. If it is not, you can go for directly the pressure losses and you can find the head loss due to pressure loss. Okay. I think here next they have given the Darcy-Weisbach equation for relation between the coefficient of friction and the Reynolds number. So I think already you have done in the earlier process. Darcy-Weisbach equation. By using these two equations, that is the head loss and the Darcy-Weisbach equation, head loss, because this also we have derived saying that this is also a head loss, okay, or the head loss due to friction in the turbulent flow or the laminar flow using this Darcy-Weisbach equation. So once you equate both of these, one can find out what is the friction factor, and that friction factor is directly dependent on the Reynolds number. To say that the friction factor is dependent on the Reynolds number, they have taken the Darcy-Weisbach equation for head loss due to friction, and they have taken the Hagen Poiseulles equation, head loss due to pressure loss, and both they have equated to explain that coefficient of friction is 16 by R, means it is dependent on the Reynolds number only. Okay, I think we'll stop the class today. Next class we'll take to the flow of viscous fluids between two parallel plates on the similar lines. In this, we are not deriving any equations, just observing the equations, what are the equations used here, and some problems we are going to solve on both the conditions. Either it may be a flow between two plates or the flow in a pipe using this Hagen Poiseulles equation. Okay. One more announcement. Here, I think I have recorded this one more chapter, that is flow past immersed bodies, that I will upload in the Google Classroom. Okay. Whereas last week we didn't take the number of classes. I think one or two classes we have missed. So for that, I'll upload that video on the Google Classroom. You can just go through that video. It is, I think, half an hour video. So that will cover our flow past immersed bodies chapter. Okay. And for the tomorrow's class, we'll discuss on problem of this chapter. Okay. See, even that flow fast immersed body is very interesting chapter for your aeronautical domain, and even this compressible flow also, last chapter. These two chapters are, I feel personally, that these two chapters will be helping you in the future also. Even the problems also have taken more realistic or very near to your aeronautical domain. Okay, so that compressible flow and flow fast immersed bodies, please focus very much so that your other subjects related